Now we will see how to find the magnetic field intensity by the different current source. For the first current source is a filament current source. Alright, so filament is actually a long conductor of very thin wires, okay, carrying a current, right? So to find the magnetic field intensity, actually we can use this formula, which is a closed integration of h dot dl equal to I enclosed. So we can determine the direction of our H field by using the direction of current cross product with the direction of our R, right? So let's say in this case, your direction of current is Z direction and the direction of your R is R. So Z cross R, you will get phi. So your H should be in the phi directions. So to solve the problem, let's say you want to find what is the magnetic field intensity along filament current source. So we draw the Amperian loop here, okay, and then looking at this figure, we can determine actually the direction of magnetic field by using the right hand grip rule, where your thumbs indicate the directions of your current and the other fingers indicate the direction of your magnetic field. So we have a different current source, such as whether we have filament, we have a surface current source, or we have the volume current source. So the solution will be the same, which is we have to draw the Amperian loop around our current source. And then after drawing the Amperian loop, we will see what is the current enclosed by the loop. Okay, so this is actually comparable with the Gauss law that we did for electrostatic. Okay, you can read here. So the direction of current is perpendicular to the loop. It's always perpendicular. The R, the direction of current, and also the direction of phi is perpendicular each other. That's why we use the cross product. Alright, for example 1, this is an example for filament current source. The question is find the magnetostatic field at distance R from I, from our current source. So this is a figure. Alright, the solution is the closed integration of h dot dl equal to I enclosed. So h, okay, dl here is basically R d phi. When you solve R d phi, alright, you got 2 pi R equal to I. Okay, it's because the Amperian loop will enclose all the current I. So our H is basically I divided by 2 pi R. And in terms of vectors, the H equal to, in the direction of phi, I divided by 2 pi R. Next, we will see how to find the magnetic field intensity for the case of surface current source. Actually, the surface current source can be in the form of a flat surface, or it can flow around the cylindrical shape and so on. It depends on the situations. Alright, in this case, for example, I would like to show you how to do the analysis of the surface current source on the flat surface. The question is, find the magnetostatic field caused by an infinite surface current on xy planes. And this is a figure. You can see that we have a very big plane on xy axis, and there is a current flow on the surface in the y direction. So the current density is written as a Js in the direction of y, and it only have a y component. So we write as a yjy. Right, so current is in the y directions. Draw a closed loop in z and x direction, because if we use our right hand grip rule, so when our current in the y direction, so it's depend on the direction of thumb, and another finger will indicate your direction of your field. So basically it feels around the y axis, which is, okay, if you see from this figure, okay, we can draw a loop from A to B, B to C, C to D, and D to A. So this is a closed loop. Ampere's law can be applied to current inside the loop. So we only consider a loop. Let go into a small loop. Okay, we take a partial of our surface. Okay, let's say we have a JS here, and we draw a loop. So by apply the Ampere's law, what happen if, okay, with the I enclosed in this case is equal to JSDL, because JS is the current density, the surface current density along the surface L. Okay, and then the H.dl is a closed loop, okay, from A to B, B to C, C to D, and D to A. So we have the first A to B, H.dl, plus B to C, H.dl, and so on, is equal to I enclosed. Later on, we see component by component. From A to B, okay, from A to B is basically, we have the H-X component. The direction is in negative X direction. So we write as a AB H.dl is equal to A to B negative X H-X, okay, because we have component as negative X direction, and our dl is X dx. So it can be simplified into negative H-X dx. And then similarly, we can analyze for Hz and Hx and negative Hz. Right, this is the complete solutions. Okay, we have Hx, Hz, Hx, Hz. Okay, we have a negative sign and also positive sign. So basically we can make it of positive, but we have to change here the limit to be the opposite. For example, when negative H, we want to change to Hx, so the limit is from B to A. This one is A to B. Same here for Hz, okay? D to A, so this is A to D. Right, equal to Js dx from B to A. Okay, let's say when we have a multiple loop, okay? So this is our first loop. This is our second loop. You can see from this figure that the Z component is always cancel each other. Right? So A minus B equal to D minus C equal to L. Hz at loop Y is cancelled by Hz at opposite loop. So this formula can be simplified as a Hxl plus Hxl equal to JSL. And further extend, we can solve this as Hx equal to Js over 2, where Js in Y direction. In the vector field, we can write as H equal to Js divided by 2 cross product with the N, where N is the unit vector normal to the surface current. Because we have the H, whether H X or negative Hx is depend on the N, the unit vector normal to the surface. let's say when negative z, so basically we have y cross negative z, we got negative x. So when n equal to positive z, we have y cross z, we got x.